Okay, well that part works anyway. Glad to have you all here this morning. This is the first in a series of 4 chemistry talks where we'll show you a little bit of what chemistry is all about. Today I'm going to try to teach you a few things, but for the most part we're just going to see some neat stuff. Okay. Some of the neat stuff is coming. And while it's coming, let me do a little survey. If I say to you the word chemical, what do you think?
A substance that can change another.
Wow. A substance that could change another. No, I'm looking for, if you hear chemical on the news, what do you think? Something good or something bad? Bad. Okay, let's think about that for a minute. The other day I went to King Soopers to get some microwave spaghetti or something, and on the package it says, contains absolutely no chemicals. What would happen to all of us in this room if we got rid of every chemical in the room? There'd be nothing here. Every one of us, everything in the world, everything in the universe is made of chemicals. Okay. So we have to realize that. Part of what I'm going to do today is going to involve some simple chemicals that that are around us every day. Can anyone name me any chemical? How about here? Water. Okay. This is water. You think I'm a brave guy for drinking a real chemical? Okay. Let's talk a little bit about water. When you're a chemist, you learn to think and realize that you learn to have some imagination that inside this little glass of water, we have a bunch of molecules. And the molecule doesn't look exactly like this, but it gives us an idea of what it is. Now, 2 guys here are white and 1 guy here is red. Anyone know what the formula for this is? Yes, in the pink. H2O. H2O. Okay. Are you sure? Now, what good do you think H2O is, other than letting me drink it?
Hydrogen and oxygen.
That's right, that's what's in it. I'm asking the question, now, what good is it?
Water.
Yes, it's good because it's water, but is it good to go swimming in? Okay, and in fact, we're going to see that. He's saying that we can break it up into its chemical elements. Isn't it good for dissolving things? Okay, let's think about that for a minute. Here I have some water. Okay. And what I'm going to do is to dump a couple things into the water. And we're going to see what's happened. One of the things I'm going to dump into the water is sugar. You want to see if that's sugar? You want to taste it? It's okay. It's sugar. Okay. The other thing I'm going to dump into the water is another chemical that we use every day and we see on a table. What do you think that is? Salt. Okay. If we could look inside one of these little particles of salt, what we would see with microscope eyes would be that it's made up of little things arranged like this. We can picture that this guy is, let me back up. Does anyone know what's in salt? Yes? No, it's not in salt, it's in lots of other things. Ah, brilliant. Okay, but salt doesn't have any oxygen in it. Yes? Sodium chloride. Wow, you people are way ahead of me. I didn't know any of this stuff at your age. This is the symbol for sodium, and it makes no sense, right? It's got to do with when a lot of the chemical elements were discovered many, many years ago, they were given Latin names, and that's where this symbol comes from. Chlorine makes some sense. Sodium chloride. Well, it turns out that in this solid, there are what are called ions. Now, I'm not going to give a heavy-duty lecture about charges, but I need you to understand one idea. Something can have an electrical charge, and each sodium in here has a positive electrical charge. The chloride has a negative electrical charge. And the thing we need to know is that a plus charge and a minus charge likes each other. But a plus charge and a plus charge they don't like each other. And a negative charge and a negative charge don't like each other. You see how this solid, this picture of the molecule shows you that? Because here's a sodium. He or she, it is a plus. And around it, the ones that are closest to it are the negatives. They like each other. And the positive guys try to get as far apart from each other as possible. Okay. Now when I throw this into water, these ions are going to say, there's a better deal for us. Rather than being in this nice picture, we're going to go float in the water. That's because part of this end of the molecule has a little plus, and this has a little plus, and this has a little minus. Who do you think? Let's ask the question this way. Suppose you're one of these guys with a negative charge. Where would you go? Green shirt. Right. You thought about coming to see you people? I'm impressed. And if you're a sodium, where would you go? If you're one of these guys? Anyone upstairs want to answer a question? How about up here?
Oxygen.
Right. One reason why water is so special is because it's got part of it that likes guys who are plus and part of it that likes guys who are negative. And so these ions can go into solution. Now you might say, well, so what? Who cares? One of the parts of the way that you hear me and you see me has to do with your nerves. Electrical signals go through your nerves. And it turns out that that's got to do with the fact that something like salt can dissolve in the water, okay, and have these ions. Electricity is nothing but moving charged things around. Now let's look at this. Before I go on, I should introduce Lynn Pierce from Department of Chemistry and Biochemistry. Who really knows how to do all these things. So if I get into trouble, I'm going to turn to her. Okay. Now it turns out that the sugar, because for the reason that it's sweet, doesn't go into these ions. So if I pour the sugar into water, nothing to see. But if I pour some salt into the water, everything I told you tells you that the These charged particles are going to go float in the water, and what do you think they might do? I've got some wires here, I've got a light bulb. Okay. This is part of the way that you work. Electricity can go through you and your nerves because of these ions. I'm going to show you another thing about ions. Actually, we'll do lots of things with these ions today, but one thing I want to start now because it's going to take a while. And that's the following. Since it's this time of the year, we have a little Christmas tree here. Can anyone guess what this tree is made out of? Let me try to get someone about here in the yellow shirt. Sugar? No, it's not sugar. I wish it were. Then we could eat it. It isn't sugar. Copper. What else do you know that's this color? A penny, right? Okay, so this is copper. And the guys who discovered this evidently couldn't spell because they call it Cu instead of Co. They weren't from CU. CU isn't that old. So here I have this copper tree that you can see. Not a great tree. And I'm going to take this stuff, which says on it AgNO3. And the part that counts for us is another one of these ions. It's another one of these things whose name doesn't make any sense. Does anyone know what this symbol stands for? Okay, right here in the dress? Silver, right. This comes from a Latin word for silver. Now, wouldn't it be nicer to have a silver tree rather than a copper tree? Okay, so we could think about maybe doing a chemical reaction. We start with the copper. We've got these guys, but we can't see them. You'll see that we can't see anything, really. It looks just like water. Is this okay? But in fact, these silver ions are screaming around inside this solution. Now it's going to take most of the time, but I'll show everyone at the end of the show what's happened. What is going to happen is that these guys are going to say, we can do a chemical reaction. And they're going to come and make silver on that tree. And at the end, we'll have a silver tree to look at. Okay. Doesn't look so great now, does it? Don't worry, don't worry. Now we saw before that when I put here it is, when I put the salt into the water, I could make a light bulb. Now who here knows who invented the light bulb? Thomas Edison. That's what I think too. But my able assistant here, Lynn Pierce, says that this is all wrong. We're all wrong if we think Thomas Edison. You know who she thinks invented the light bulb? You'll never guess. She has to tell you.
I think that Mr. Vlasic invented the light bulb.
Anyone know who Mr. Vlasic is? Okay. Maybe he didn't invent the pickle, maybe he did, but certainly we think about him in pickles. So here we're going to test the idea of Lynn Pierce.
Here's a classic light bulb.
Okay.
You have the house lights down?
Yeah. Now before I do this, did anyone have a pickle yesterday? Or a day before yesterday? Did it taste salty? Did it taste moist and wet? So what do you think is in this pickle? Water and aha. Have we seen that before? Maybe this has to come on.
It's a very dim, slow light bulb.
But still it's a light bulb, so she was probably right. So we'll give her a hand. And the next time you eat a pickle, you should be careful because you might be eating a light bulb. Okay, now, a few minutes ago when I said what was water, somebody over here, I think, said it was H2O. Now, how do you know that? Is it because if you go to King Soopers, you'll see some bottle that says H2O on it? How do you know that? You learned it in school, but maybe... Okay. That's all right, too. You learned it in school, but how did they know? Someone told them. But how did... You see how it goes. How did someone ever figure out that this was originally H2O? I'm going to show you. Let's think it through. Someone else over here said that if we took water and broke it apart into its elements, well, he or she said it was good because we could take water and break it apart into its elements. What are the elements that are in water? In the back. Yes, you. Hydrogen, right? Oxygen, right. Okay. If we say H2O and look at this picture, we should, when we break it apart, we should get twice as much hydrogen than oxygen, okay? That makes sense? Everyone see that? All right. Well, slowly, while we've been playing around here, we have this machine that's doing a bunch of work to take the water molecules and break them apart into their elements. And can anyone see that, in fact, I hope you can all see. Lynn, is it visible? No? Professors always have paper ready. Maybe this is better. Can you see that? Okay. What's happening is that the water, Lynn is going to show you around the audience. The water is being broken apart by this working machine here. And hydrogen and oxygen are gases. And the gases are collecting at the top here. And what we see is on this side, you can't see the gas, but you can see that the gases push this liquid away. What we see on this side is we've got about twice as much as we have on this side. Okay? Now I get the idea that even though it's this kind of thing, that lets us know that water really is H2O, not because someone told us, because we can find out for ourselves, and that's what scientists do. Maybe you're a little bored with this. You're a little bored with this? Yeah, this guy's yawning. Okay. All right, let's do something more interesting. I'm going to draw a picture of what was done in this machine. Here we had some waters. And here we have some oxygen. It doesn't matter. I'm just trying to show that these atoms are hooked together in a molecule. The details won't worry us too much. Now that machine, we had to plug it in and make it do some work. The water molecules want to be water molecules. They're happy here. Very happy. The work we did is, we can understand it in terms of, well, suppose we had to go up some sort of hill, all right? Everyone in Boulder understands that idea. And these guys, you think they're as happy as those guys are? No. They're pretty happy. But they're less happy. Now we had to push the water to break it apart to make these things, the elements. How about if instead of going this way, we went this way? A scientist would say, wouldn't talk about being very happy and less happy. They would say, this is low energy, big happiness, high energy, not so happy. Let's think about doing the reaction this way. See this? It contains hydrogen gas. Let's think about the name hydrogen. Gen is like genesis or generate, gives birth to. Hydro, what do you think that means? Water, hydroelectric plant. So the name of hydrogen is to give birth to water. Here's the water down here. Here's the hydrogen. What else do we need? The hydrogen is in here, in the balloon. Where are we going to get the oxygen? It's in the air. About 20% of this air is oxygen. So let's see what happens. Where's... Okay. Before I show you this, I have to tell you something. This machine had to put in a lot of energy to push up here. But when we come backwards, the energy is going to come back out. And we'll see how it comes back out. And part of the way it comes back out is you're going to hear something. Earplugs. What you should do, if you don't carry earplugs around, is cup your hands, put them by your, I can't hear myself, put them by your ears like this, okay? Do we need the lights on? To see that? I can't hear you. I'm going to turn off the microphone. You ready? question. Ah, good question. The question is, where's the water? Now you have to believe me that the water was made there. But would it be easy for us to see it? Wasn't this kind of a high temperature because of all the energy came out? And what would happen to water at high temperature? It would vaporize. It would turn into steam. Easy to see steam? No. Okay. So it happened, but we'd have to do the experiment a little more carefully to actually see the water. So you have to take my word for it that it happened. On the other hand, if we did it more carefully, you wouldn't have seen a big flame and a big boom. Okay. Now, one of the ways that chemicals are used in the world, not only to let our nerves work and our bodies run, but to provide sources of energy. So we saw here was a reaction that gave out some energy. Can you think of anything you might ride around in occasionally that uses energy? Here? A car. And how does a car work? Up here, yes? Gasoline. And what happens to the gasoline in the car? Back here? It gets burnt. There are little explosions of the gasoline in a cylinder, and the explosion pushes up the cylinder and it makes the wheels turn, and that's physics. I don't know any of that stuff. What we're going to do is to show you not gasoline, but ethanol. Where is it? Okay. So here's the idea of a car. Each of these things has a little bit of ethanol in there. And the ethanol is going to react with oxygen, just like the hydrogen reacted with oxygen. Okay. What we're going to do is do the chemical reaction of ethanol with oxygen. And what do you have in a car that makes it work? The spark plugs. It gives us a spark. We've got some spark plugs here made of nails.
Can we have the house lights on, please?
You ready? Some more? All right. Okay, now we've seen a couple of things where the chemical reactions, starting from one molecule and going to other molecules, gave out some energy. Okay? Could it be that some chemical reactions will work by going uphill, climbing up the hill all by themselves? Instead of... There's trouble on this side all the time. Let's think about this. What we've seen is chemical reactions going this way, giving out energy, making the flames, showing the explosions, the hydrogen, they all did that. Suppose we had a chemical reaction that went up the hill. It went from here to here. Where is this? I'm going to show you one that does that. This is something called barium hydroxide, and this is something called ammonium nitrate. And when I mix the two together, they're going to make new molecules. Now, it turns out that this reaction, there isn't going to be much to see inside because the molecules that are made are also white. So we're not going to see too much. But if we think about reactions that went the other way, we saw energy come out. What did we see? We saw some flames, which is one way we can see heat. So if we do the chemical reaction in one direction, it gives out heat coming down the hill. If we're going to go up the hill, what should happen?
Be real cold.
Very good. It's going to be real cold. So let's try to do something with that cold. What happens to water when I make it real cold? Make some ice. Okay, so here I've got a wooden block. Here I've got some water. I'm going to smear the water around on the block. And now I'm going to do the chemical reaction. And I'm going to help it along by introducing the molecules to each other, by stirring them up. Now I need a volunteer. There'll be more volunteers, don't worry. Now I want you to touch that and tell everybody what you feel.
It's cold.
It's cold. Now what should happen to the water underneath? It should freeze. We already decided that. And if it freezes, what should happen? Might stick. Ah! Do I need some more water then?
More time.
More time. Maybe I need to introduce these molecules to each other a bit more. I don't think this is going to work. Maybe it needs a professional touch. Okay. Okay, well, these chemicals have a mind of their own sometimes. We'll let it try to freeze for a little while and come back to it, okay? But don't let me forget it. Promise you'll remind me? Okay. You've seen two chemical reactions that involved oxygen. Now we're going to do another one. And what we're going to do is right here, and it involves two things that we can see. One is magnesium metal, which is well, here you can see it, magnesium metal. Looks like any other metal. And we're going to do a chemical reaction of magnesium metal with this, with inside a covering that looks like snow. It's very cold, but it's not snow. Anyone guess what it might be? Up here with the baseball cap?
Styrofoam?
No, it's cold. It could be cold styrofoam, you're right, but it isn't cold styrofoam. Up here in the red, dry ice. Anyone know what dry ice is? What chemical it is? Pink shirt? Carbon dioxide. CO2. What we're going to do is burn the magnesium. And when you burn something, it means it's reacting with oxygen. But what we're going to do is cover it up so the oxygen from the air can't get in. So I want you to think about the following. The oxygen from the air can't get in to help burn the magnesium metal. The carbon dioxide, which is cold, is CO2. So think about where the oxygen might be coming from. We need a light out?
After we get it lit.
When I get this lit, I'll need the lights out. Okay, I'm going to start off the magnesium if I can. See it burning? Oh, it's burning. Ooh. You shouldn't show them the trickling. Okay, have you been thinking about my question? The question was, the magnesium is burning, which means it's reacting with oxygen. We covered it up, we didn't let the oxygen of the air get in there. Where's the oxygen coming from? Back here in the, yes, you. Okay. Everyone agree that the oxygen is coming from the carbon dioxide? Can we think of a way to test that? If the oxygen has left the carbon dioxide, what's left? Carbon. What color is carbon? Doesn't look black, someone says. They're always doubters. Science is tough because they're always doubters. Okay, so we're going to let this cool, and I'm going to get a volunteer to look inside. Well, I'll ask for Bob. Bravo. Okay. We got to see if it's cool enough yet. Lynn? Okay. Were you a volunteer before?
No.
Okay, come on, please. Now, what do we expect to see if this lady in the back was correct? We expect to see something black, right? Did we put anything in here afterwards, after we burn the magnesium? No. Nope. Okay, so I'll, if I may. You have to tell everyone what you see.
I see a big hole with black and white stuff in it.
Okay, but you see the black. Thanks a lot. If I look in this room, I see that this girl has on some red. This guy has some green. Oh, I'm sorry. I need new glasses. I'm sorry. I usually can tell the difference. It's the excitement of the moment. Yeah, I was blinded by the magnesium light. This looks brown, black, pink, blue, yellow, all these colors. Why do you think things have colors? So you can see them, but where does the color come from? Fibers, but what's in the fibers that gives them the color? Dyes, but what are dyes? Chemicals. In fact, all the colors we see around us are somehow due to chemicals. It would be kind of a boring world if we didn't have these colors, right? Okay. Now I'm going to show you a bunch of things having to do with colors, and we're going to start out with a simple one. Where is it? Ah, it's here. Now before I show you this, I need to talk to you for a minute about atoms. I'm going to give you a little cartoon of an atom. It's a picture that everybody sees. Everyone recognize a picture like this? Okay. Who's buzzing around here? Yes? An electron, okay. Now what I'm going to do with this machine, which is an electron exciter, is I'm going to give that electron some energy and make it not do this, but do something like that. Now this is like, it should remind you of putting in some energy, doing some work to take something from very happy to less happy. Okay, so after I zap these atoms with the electron exciter, the electrons are going to be, in some sense, it looks like a good time. But the electron would rather be back down here. And the way it does that, it gives off some energy. And what do you think that energy is? No volunteers up? Light. It gives off certain energy, certain light, and certain light is what we call color. So here we go. Lights, please. I'm going to start with a molecule, but it's the same idea. And in here I have nitrogen gas. That's about 80% of the air around us. So let me excite the electron. And they'll be happy again. Okay. Now comes, it's so dark I can't tell what it is. Hold on, it's all right, it's all right. Helium. Where do you usually see helium gas? In balloons, right? Okay, now it's in here. I'm going to excite its electron. Bong. Here's another gas called argon. It's a different electron, so it's going to show us a different color. Here's mercury gas. And here's a mystery gas. We lost the label. We don't know what it is. But it's a nice color. All right. Lights, please. That's one way to get color, to excite the atoms or the electrons in the atoms of the molecules, and then they put out the light. There's another way that is the reason that things are colored. And I can explain it this way. The light all around us is white light. And does everyone know that that means that it's got all the colors in it? Okay. And when it hits the molecules will eat up some of that light to excite the electrons. And then what we see on the other side is missing some color. And if some colors are missing, that means we see the other colors. Exactly right. Very good. Now what I'm going to do is to make different molecules which, because they absorb different colors of light, we are going to see different colors. And these are molecules that contain nickel. Nickel from the nickel, it's nickel metal. That's an element. I don't think there is any in a nickel anymore, but there used to be. And all of these are kind of cool molecules in terms of the way they look. The nickel sits here, and different things hang off of them. The first one we have will be water, 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 water. And by pouring various things in there, we're going to take off the water and put other things on there. All right? What's first?
First is just nickel.
Okay. So here is the one. Here is a solution of the molecule that's got a nickel in the center and a bunch of waters around. Nice green color. I like this one a lot since I'm Irish. Okay. Now, we're going to do some chemistry magic and take off the waters and put some other molecules on there. And we'll start with ammonia. You know ammonia from household cleaners? Doesn't smell so great. Okay, so now we've got nickel with a bunch of ammonia molecules around it, and it's blue.
I poured you for the first one, that's ethylene diamine.
Okay. Here is another molecule called ethylene diamine. Doesn't matter what it's called. It's going to make a new one. We should see a different color. Okay, it's a different color blue this time, because it's a different molecule. Question? Okay. Different one. Grape juice color. Another one. Someone want to do this? Just pour it carefully. Thanks. Looks like the same one to me. Is this a different one? I'll hold this, and you pour this. Oh, look at that. All right. Born chemist. One more. No, this one's a little bit dangerous, so I'm going to do it. It's a little dangerous. All of it?
All of it.
Okay. I'm going to do what you told me. Okay, a yellow one out of that. Okay. Lemonade yellow. How many here have been to the fireworks during the summer? You notice that a lot of the fireworks are not just white, they have different colors? And the way that that works is that inside the fireworks are different chemicals that have the different colors. And we're going to do something like that now.
Okay, all you have to do is light them.
Lights, please. What we have here, in each of these little dishes, we have a solution of a different chemical. The first one is a lithium salt. It's got the Li plus guy floating around in it. And we've got some alcohol. So you can see what happens. Okay. I'm going to light them all so we can see all the different colors. This is sodium. This is, what is this? Calcium. Calcium in your teeth and bones. This is strontium. This is copper, our buddy copper. And this one is barium. Lights down, please. All right, I have two more things to show you. The first one is also related to the time of year. Let's actually have three more things. Remember that we started out the Christmas tree, and I told you that we were going to do the chemical reaction where the silver ion came out and made silver metal on side of the copper. Everyone see this? See the silver? Okay, you can come down afterwards and see the silver if you can't see it here. Another tradition of this time of year would be to light candles, so let's try to do that. And the way I'm going to do the candle lighting is from a distance. I'm not going to use a match. What I'm going to do is to take some alcohol and pour it on chromium oxide. Lights, please. From a long distance. My eyes are not so good. We already established that. The question is whether I can do it. I could do it. All right. Final thing. Let me tell you about who are the guys playing the game of this chemical reaction first. Anyone know what this is? Girl with the long hair? Aluminum. Where do you see aluminum? Aluminum foil. This is iron oxide. Anyone know where you see that? Rust. This is rust. Now it turns out that the aluminum would rather likes the oxygen more than the iron does. So the chemical reaction you're going to see is the aluminum metal stealing the oxygen from the rust. If we take all the oxygen from the rust, it was totally stolen, what do we have left? Iron metal, like a nail. Then we're going to get something called aluminum oxide. Now this is one of those things where we start up here kind of happy, and we end up here very happy sometimes, but there's a lot of energy going to be given off. And the energy given off is going to come in the form of light and heat. And there's going to be so much heat that we're going to melt the iron. The iron is going to melt. The iron is going to melt, and it's going to be so hot it's going to eat out the bottom of the flower pot and fall down into here. Okay.
We always like to use the hot iron to do something useful. So we can either crucify a soda can, or we can bury a little brass statue of the Cornhusker.
What's she talking about?
Okay, he's ready. He's brave and stupid.
I told you chemistry was tough. Okay, lights out, please. The first thing you're going to see is me attempting to light a magnesium fuse, which will start this chemical reaction. It's not going to make a bang. Get back, kids, please. Everybody back. You're okay. Here we go. Do you see the liquid iron melt down? Okay. Okay, we've just had time today to show you a few thrills and chills from chemistry. There are many, many more. Season's greetings to everybody.